Okay, right. What we are going to discuss here is the following. Okay, let's start by drawing a circuit. Now, what's the objective of drawing this circuit? This circuit constitutes as what we would call a single phase circuit. Okay, right. Now when I say single phase, there's something I want you to pay attention to. Okay, when I say pay attention to, simply meaning single phase, there's nothing special about this, there's nothing new about this. However, there's something that we have to point out with regards to single phase, and that will be the following. Okay, over here you have a wire. That wire has a resistance. Okay, over here there's also a wire. This normally is your return path. Guess what? That also has a resistance. Okay, and then this over here will just basically be our load. Okay, right. Now notice this will be our voltage source. Now notice what I'm going to do next. Okay, what I'm going to do next is the following. I'm going to make a claim. My claim is the following: the power in a circuit is equals to the voltage multiplied by the current, okay, in that circuit. This is the claim that I am making. Okay, now from this claim, yeah, we can therefore say that current is equals to power divided by voltage. Okay, now when we say power, what normally are we referring to? We are referring to what? The power across the load, voltage across the load, current through the load. Okay, so those subscripts, they basically mean what? Load. Right, that's a claim. Now this is a claim where it should be obvious. Okay, meaning it should be true. Okay, meaning there's nothing to debate or discuss with regards to that claim. Why? Because it's fundamentally true. Now let's continue. Okay, what do we know? We know that this wire over here, for now let's call that the live wire. For now let's call this the neutral or the return wire. Okay, what we know is when we look at the power loss due to this wire, power loss due to that wire. Why? Because that wire has a built-in inherent, or what we call internal resistance. Okay, that can be equated as power loss. It's I squared over R. Now when I say power equals I squared times R, again this is an expression of power. In this case, what power? Power loss, meaning power that's lost, okay, due to wiring or wiring resistance. Okay, right. However, how many wires do we have in here? We have 1, 2. So this is going to be what? Times 2. Right, there we go. Now here's the thing. Catch this, because this is powerful. What's powerful there is that this can be written as 2R, okay, I squared. So this will be 2R. What's I? I can also be written as PL over VL. So this is what? PL over VL. What did we say? We said that this is what? Load. Okay, so this current here is the current that flows through this conductor, and that current is equals to what? It's equals to the load current. That is why we can say load is equals to PL over VL, meaning P load over V load, and that essentially is this current over there. Okay, right, and that is what squared. So simply meaning, what did we accomplish here? What we accomplished is by understanding that power loss due to the wiring is equals to 2 times R times PL squared over VL squared, where PL is the power due to the load, and then the voltage due to the load. Okay, right. Obviously this at this point in time it doesn't make sense. However, but because we are heading somewhere, as we get closer to our destination, hopefully then it will make sense. Okay, right. Now we'll do the same thing. This is IA, this is IP, and then this is IC. This is what we call a three-phase system or a three-wire system, okay? Here's an assumption. The assumption is IA is equal to IP, and that is equal to IC, okay? Now, another thing that we can claim is that the power across the load is equal to the square root of VL times IL. Okay, we can also say cos phi, then we can say that phi is equal to 0 degrees. Therefore, our PL is equal to square root of 3 VL IL times 1. Why? Because if you say cos of 0, it's equals to 1, right? So therefore PL is equal to square root of 3, it's equals to VL times IL. Now this is a claim we are making, okay? That's true with regards to three-phase circuits. Okay, now let's continue. We can say that P loss is equal to I squared times R. This is now the power loss due to wiring, not load, in this case wiring. Okay, however, how many wires are there? From the sketch drawn here, there's at least 3 wires. Okay, so then we will say times 3. It's important to note that the current here, it's also what we call I load, because it's the current that goes through or via the load. Okay, so now we'll say 3R times, what is IL? IL is equals to PL square root of 3 VL. And then what's this to the power of 2? Square root of 3 times square root of 3 is equal to 3. 3 divided by 3 is 1. So in this case, we will have R, we will have PL VL squared. Okay, now here's the question. The question is, what exactly is it that we are trying to achieve over here? What we've done so far is, for a single phase circuit, we've managed to prove that power loss is equal to this expression. Okay, when I say power loss, I'm referring to power loss due to wiring. Okay, yeah, this is a three-phase circuit. Same thing happens. We've successfully managed to get an expression that will express the power loss due to wiring. Okay, and in this case, here's the expression. So this is the expression for three-phase. That's the expression for single phase. By expression, I mean power loss expression. Okay, right now let's go deeper. Let's go and let's determine the ratio of power loss in single phase relative to power loss in three phase. Okay, and then this ratio, what do we notice? We notice that this ratio now what? It's 2R PL over VL squared. That's where we are getting it for single phase. Okay, and then here's the one for three phase. All right, so we divide by the one for three phase, which is R PL VL squared. This cancels out, and then this relationship, it's what? It's a 2 to 1 relationship, simply meaning the ratio for power loss, this is what single phase relative to power loss due to wiring for three phase, it's what? 2 to 1. Now what does this mean? Okay, what did we accomplish here? What we basically accomplished now is we have proven that the power loss ratio, it's a 2 to 1 ratio, meaning your power loss of a single phase circuit relative to a three phase circuit, it's 2 times more. That's it. Simply meaning, due to the wiring, my power loss across a single phase system, it's twice that of a three phase system. That was the objective here. And hopefully, if you now reflect back on that, that would make sense to you. So yeah.